In previous videos, we discussed the atmospheric equation, also known as the equation of momentum, which, in simple terms, just looking at the main force we have, for example, the u velocity equation, we have du dt, so u is the velocity in the x direction, is equal to -1 over the density times the change of pressure in z, the vertical coordinate, plus other forces. So this equation is an amazing way to calculate velocity changing over time. However, once we get to the next time, we don't know the new density and the new pressure to do the calculation again. So we need to find a way to calculate both of these. And so that's where the mass continuity equation comes in. And the mass continuity equation is basically a mathematical expression for nothing can be destroyed or created, which you may have heard before. And so in 1755, Euler said that he found that the fractional rate of change of specific volume, which is the inverse of density, is equal to the velocity divergence. And the fractional rate of change is defined as some variable. You want the fractional rate of change of f, you would have that it's df dt times 1 over f. So it's the change of that variable divided by what it is currently, or divided by what it is currently. And here's how the way of thinking for how did he know its velocity divergence? So this is what he's saying here. When this value is positive, that means things are diverging, which means if the region's at the dot, they are leaving the region. So you can think of some mass as being taken by the velocities and move in or fluxed out of this location. And so if this increases, that means that this specific volume term must be increasing over time. This must be positive. So if this is increasing over time, that means its reciprocal, which is density, which is 1 over it, is decreasing over time. So that makes sense. If velocities are diverging away, that means the mass is getting taken away and moved into another location, and mass could be moving into that same location. That's why nothing is getting destroyed or created. And so what we can do is we're interested in this term here. We want the change in time of density. And since when we want an equation, we want to know the change with the partial derivatives. We don't want to use these total derivatives because they're not. We're not able to get rid of this advection part, so we need to take that out. So what we'll do is we'll start with, we know that this is equal to this from other videos. And what we know is that this specific volume is equal to rho to the -1, or 1 over rho. So we can just interchange these. And by law of logarithm, ln of f is equal to ln of f to the -1 is equal to negative ln f. So we take that -1 right outside of the derivative, because d negative f dt is equal to negative df dt. So that leaves us with this d ln rho dt is equal to negative instead of positive, negative divergence. We also know we can expand this term into the total derivative term into the partial derivative rho partial t plus the advection of density, which is basically the moving of density over space. And what we can do is we can multiply this rho on both sides. That gives us this term, and then subtract this term now, which will not have a rho by it anymore, and and it will look like this. And I also took out the negative when I did that. And there is a rule in vector calc that is as follows. The divergence of a constant, so a is a constant, times a vector f is equal to f vector dotted with the gradient of a plus constant a times the divergence. And we see that here's a vector, here's f, here's a, so we have our a divergence term here. Oh, and sorry, I wrote that in a weird way. That's an f. Okay, so here we have f gradient, the constant, that's this term, and this term is the constant times the divergence, just as in this case. And so we can see that this whole thing is just this term. And that's exactly what we have written here, and it's negative. So this is our equation for the mass continuity. The partial change in density over time is equal to the negative divergence of the density times velocity. And now for the second method. A lot later than Euler, Holt in 1979 derived but this same equation via the mass balance for a small volume element fixed in space. This is a more fundamental derivation, while as the Euler's version kind of stated something that sounds obvious but doesn't really have any fundamental understanding of calculus that comes in here and explains in a physical way how this is working. So what Holton did is he started with a infinitesimally small mass change. So delta's change. So the change of mass is, and from one location you have a certain amount of mass, another location you have a certain amount of mass. If this location has more than this location, then delta m is bigger. Then at delta, you can say m2 is greater than m1, then that delta m would be, much more bigger than it would be then, So we know that rho is equal to mass over volume, so mass is equal to rho volume. And, if we have mass equals rho volume, then we can add this sign delta, so we would get, and of course delta rho doesn't really mean anything. You can put the delta inside, you get delta m is equal to rho delta v. That's this. And we know that delta v is equal to delta x times delta y times delta z. And so you can imagine it like this. You have this little box, and maybe this is delta x, this is delta z, and then inside you have a delta y. And from the statement that nothing can be created or destroyed, we know that the total derivative in time of this delta m should remain 0. And so we plug in our statement here, and then we do the chain rule, which is basically like this. If you have d, a, b, c, for example, or d, a, b, where a, b are functions, dt, you would have a, this would be the product rule, my apologies. So we're going to apply the product rule. And that is basically saying that if you have dAB dt, you would get a dB dt plus b dA dt. And in this case, if we step it up, here we have 4 terms, but we're going to end up, getting to 4, but let's just show you what 3 will be, and then we'll do it over here. So ABC would be equal to A times the, let me see, right, A times the derivative of BC dt plus B times the derivative of AC dt plus C times the derivative of AB dt. And then you do the chain rule again, or the product rule again and again. So I'll just show you what that looks like. So, okay. So we do the first term. We have delta d rho dt times the constant of everything else, so that's dv, of course. Then you do rho, take rho out, times the derivative of the inside. And so we have a situation where we have 3, just like I just showed, and that will be like this. You will have the derivative of the first one, dt, times the other 2, plus the derivative of the second one times the other 2. So derivative of this one times the other 2, and finally the derivative of this one times the other 2. That's what we have here. And we can do a little bit of further steps to this term, for example. So we can take the delta out, so that goes here, and we have delta times dx dt. And but when we take out the delta dx dt, let's see, we should also have a term that looks like this from the product rule. This time, not the product rule, this time is the chain rule. Let me write that better. The chain rule. Okay, so this term will have dx dt, but we also need the chain rule, so it's going to be delta x partial x. Okay, so, we can simplify these since they're just a repetitive kind of version of, well, let's just write it out in full just so it can be more accurate. This one would have delta y partial y. And then this one, we're going to have delta z partial z. So for this, back to this one, we have delta, and we know that this dx dt is just equal to u. And then, so we have delta u, and then this term remains. And you can, write this as delta u divided by partial x. And if you notice, every time we do that, we'll have, the delta u partial x term, and then delta x. And delta x times delta y delta z, that's just delta v again. This one, the delta y term would go here. This time, the delta z term would go here. So we can take that out, and we're left with this term. Now, this line. So we can, because we know this is equal to 0, we can divide by delta v on both sides. And this right here is the divergence. If we take the limit as, these things go to 0, this delta u is just going to become partial u. So we'll get the divergence term. And if what that looks like is d rho dt plus rho times divergence is equal to 0. So this is our, closed form of the equation, but we can further simplify it again in a similar manner as before. We break down the total derivative into a partial derivative over time plus advection term, and then we make the manipulation to move this thing onto this side. We combine, and we use the rule from vector calc to get that the negative divergence of density velocity is equal to the partial derivative of rho over time. And you may have seen, if you've ever looked up the Navier-Stokes equations, that there's a form of the mass continuity equation that is included that looks like this. Divergence of v is equal to 0. And that is only true in a specific case. That is true in the case that the change of rho over time is equal to 0. So we're saying that the density is in other words, we're saying that density is a constant. So if this goes to 0, we can move the negative onto the other side, and we'll get 0 is equal to, or the divergence of rho v is equal to 0. Rho is a constant now because a change in time is 0, so we get divergence of v is equal to 0. But that is only true if density is not changing, and density for sure changes in our universe on Earth. So this is the acceptable form of the equation. And in the next video, I will discuss the moisture continuity, which uses this equation combined with a similar equation in a similar form that includes Q, the mixing ratio of any sort of mixing ratio. It could be QL, it could be QI, QC. This is liquid, this is ice, this is cloud. There's many other ones. There's QW, QR. There's many different fractions you can break air down into for moisture. And we'll get two equations, and then we'll use this equation to, we'll get one equation for moisture continuity like we did in this video, then we'll get this final form included in the mix, and it will give us a moisture continuity equation. And at that point, we will have completed the set of equations, which, just as a quick sneak peek, are the momentum equation, or atmospheric equation. And then we'll have the mass continuity, and then we'll have the thermodynamic equation, and then we will have the moisture continuity. And that will be all the equations that we'll need to model the atmosphere, and there are some things that will need to be researched, have already been found out and are currently being researched to complete the source sink term of these equations, which hopefully, if I learn more about that, I'll discuss it on this channel in the future. So thank you, and stay tuned for the next video.